Okay, if you can't tell just from the immediate start of this video, I've got a cold, but I also have pink eye, so I'm not gonna be there. Don't want to spread that around. I shouldn't be contagious anymore, but you know, we want to take that risk. Anyway, I'm gonna walk you through the rest of the project. So I'm gonna start at this page. This is the page that you will get to after you've done the crossover calculator. If you missed the day where we did the crossover calculator, you just need to Google search. Just Google search the words crossover calculator. I'll write it there so you know how to type it. And you can ask a neighbor also as well what it looks like. And it'll probably be the first link. It's like DIY audio something, whatever, crossover. Anyway, there's a process to like select components, and you got to ask classmates because I'm not going to go through that in this video. Once you've done that crossover calculator, it will spit out to you some wiring diagrams. And what I'm having you do is drawing your wiring diagrams on this paper using these symbols. This for resistor, this for inductor, that for capacitor, that for speaker. In the wiring diagrams, there's no resistor. It's just these. Eventually, we're going to consider our speaker to be mostly a resistor in our circuit. So here's an example of the wiring diagram being changed into a schematic for the high frequency. So this would be like the tweeter, is what it would call it. And then this would be an example of a third order. So you have option between second order and third order being exceeding. Okay. Let me pause the video here. This would be a third order, and it would be a woofer or low frequency. Okay. So again, work with your classmates to figure out what these are, and then we need to translate them into these sort of schematics. Then what we're going to do is we're going to take these schematics, we're going to rewrite them, and we're going to do two things to them. One is that these images of like our speaker, this is like a wiring diagram. We're going to change those speakers into resistors. So it's going to be a 8 ohm resistor, a 4 ohm resistor in our schematics. So you can see, here's an example of a tweeter right here, where the speaker has been replaced with the resistor. This doesn't perfectly match this side. It matches what's on the board, the diagrams that are on the board. So, so you're going to do that. That's number one. And then the other thing you're going to do is this will spit out values, 0.88 mH or 4.56 UF. Those values don't exist over here in my classroom. They're not part values you could actually grab. Nothing's that precise. So we want to figure out what we will actually use when we go to make it. And that's what the values that we'll write down. So you can see here, I've got all of these values are things that I can make. And in some cases, I couldn't make them directly. For example, this 7 mH inductor, well, there isn't a 7 over there. There's a 1 and a 6, so I could use a 1 and a 6 to make it. So I wrote 1 plus 6 to remind me when we go to make it, that's how I'm going to make it. I'm going to use a 1 and a 6. Same thing here with 55, 22, and 33. Those existed, but 55 did not. So anyway, the goal is to get close. If you're within 10%, it's close enough. It's pretty easy to get within like 5% most of the time. And so there you go. Does not have to be perfect. You're just trying to get close. And then this is an example of a schematic for a 3A-way system, where this is the high, the tweeter. This is the mid, which we'd use a woofer in this situation. This is the low, we'd use a subwoofer in that situation. This would be an example schematic of those. And then I also want you on this paper to also write in the crossover frequency or frequencies. If you're using a two-way system, so you just have a low and a high, you don't have a mid, well then you just have one crossover frequency. That's a frequency you entered into the calculator. Again, if you were gone and weren't here for that time, we put a frequency between 150 to 250 hertz if we were dealing with like a subwoofer, a crossover from a subwoofer to a woofer or coaxial or anything like that. So if a subwoofer is involved, in that crossover point, we want it to be low. And if a tweeter is involved, so this is for like if a sub is involved, if a tweeter is involved, well, that's high frequency. We want that to be much higher. So we made that 1500. I'm not exactly remembering the exact ranges, but I want to say it was 1500 to like 4000 or something like that hertz. Okay, somewhere in that range. Anyway, you make the call, you write it down. Okay? All right, from here, the main point of this video, other than to remind you where we're at and get you started, is to show you how to write the equations starting from here. So, first, these equations exist on, you don't have to like write them down again. They exist, I want to say the best place to find them is, on the very back. Here's the voltage divider equation. We're going to be using this because we have V in and an output in the middle. Okay. Here's the form for parallel. It's 1 over the first one plus 1 over the second one to the negative 1 power. Here's the equation for the inductor. Here's the equation for the capacitor. Resistors don't have an equation. They're just what they are. Here's the metric prefixes, all that. So all of this stuff that I'm about to do, I'm just taking all this information back here and working it out in each problem. So, but you can also just follow along. You'll likely have a pretty similar circuit to mine. It just part value changes. So let's focus here on the high. So here's where the signal comes in, and the signal comes out where the speaker is. This is the speaker. So there's my in, there's my out. Well, this is a voltage divider, and the part between my in and out is called Z1, and the part between my out and ground is called my Z2. And the equation for a voltage divider is always V out equals V in times Z2 over Z1 plus Z2. That's the equation for a voltage divider. Now, we said two things that we're going to do to simplify our problems. Number one, we're always going to consider Vin to be 100% or full volume, meaning it's not being made louder or quieter, it's just flat. And 100% as a number is 1, and 1 times anything is itself, so that just, we can omit it. We don't even have to write it. The other thing we're going to do is we're going to put absolute value around the whole thing at the end, because when we graph it in Desmos, we don't want like 3 4-dimensional graphs. We want a two-dimensional graph, frequency and volume. That's it. Those are the 2 parameters that we want. And so that's what we're going to do. Okay, so how does this work out? So first I look at Z2. That's this bottom part, which is 2 things in parallel. And the way that you do something in parallel, again, this equation is on the back side of this sheet of paper. You can go reference it. But so I'm going to start this equation where I go V out equals. And in the voltage divider equation, Z2 is on top. So this is Z2, and it's parallel. So what I need is a parentheses. Oh man, just picked the exact wrong time for my nose to start really running. Anyway, continuing on. We start with parentheses, this is a parallel circuit, and we go 1 over the first one, which I'm going to pick the speaker to be my first one, just because the numbers are simpler. So it's just 8 ohms, so I'm going to do 1 over 8. Okay, and then plus 1 over the next one. Well, what is the next one? It's an inductor. An inductor's formula, so I go 1 over. An inductor's formula goes 2 pi f times the inductance, which this inductor is 1.5 milli, which is 10 to the negative third. And then I always add a j at the very end. Okay, and then I end those parentheses. Negative 1 power. That's because they're parallel. So when they have 2 things that are parallel, 1 over the first plus 1 over the second to the negative 1 power. Okay, and then the on the bottom of this fraction, it just goes Z1 plus Z2. So Z1's up here, and the equation for a capacitor is negative. So an equation for an inductor is just this. So I had 1 over, and then I just wrote that. And here I have a capacitor, which the equation for a capacitor is negative 1 over. So I need to write that whole thing. Negative 1 over 2 pi f times the capacitance, which in this case is 5.6 times 10 to the negative 6 J. Getting that 5.6 times 10 to the negative 6 from there. Okay, so there's my capacitor. That's my Z1, the top part. And then I just add in the bottom part, Z2. Well, that's so much. I'm not going to write it again. I'm just going to write the word top. Okay, and at the end, we take this equation, we put absolute value signs around it. Okay, that's what we're going to write. Now, for the high frequency, which I'm going to show you right now, we're going to skip the mid till the end, like the end of this video. I'll do the mid equation with you. But if you haven't done so already, pause this video, make sure you do your, wow, I just wrote the high frequency equation. Well, yeah, if you do the same thing with me, then yeah, just cross this out. Anyway, so this is my high frequency equation. And so there we go. I'm going to write my low frequency equation. So it's my high frequency. I'm going to go write my low frequency. And then we're going to graph it. I'm going to show you that process. And then I'll come back to the mid. Okay, so we'll do low, which I scratch off here. Congratulations if you caught my mistake and didn't make it. But whatever. So we're going to do V out equals. And it's always Z2, which is this bottom piece. It's the thing from V out to ground. Everything in here is Z2. Everything between V in and V out, that's Z1. Okay? So the equation starts with Z2 on top, which it's going to be another parallel thing. In fact, it's going to look a lot like this, but instead of the inductor being right here, there's going to be a capacitor. And instead of capacitor being right here, there's going to be an inductor. It's just going to flip-flop. The values will be, from the schematic, but it will be very similar. So I go 1 over my speaker, so I got parentheses, 1 over the first path, which is the speaker, plus 1 over the second path. Now, the second path is a capacitor, and the equation for a capacitor is already a fraction. So when I do my 1 over, I then need to put the equation of the capacitor, which itself is a fraction. 2 pi f times, is that 55 UF? Yeah, 55 times 10 to the negative 6 J to the negative 1 power. Oh, wow, that's off screen. I am so sorry. So it's 1 over this one, 1 over 4, plus 1 over that one. That's a capacitor, so it's 1 over the capacitor formula itself is a fraction. Okay, so we just write the fraction down below. And then we go, so that's Z2. Then all over Z1 plus Z2. Z1's an inductor. Okay, so I got to write 2 pi f times my inductor is 14 millihenries. And then I got to add Z2 again, which is what the top was. And so I'm just going to write the word top. Okay, we're going to end it there. Okay. If you're doing the median level, like this is your two equations. If you're doing the three-way system, I'll show you at the end, the mids. It's quite a lot. I'll show you. You can do it. It's possible, very possible for everyone to do it. If you're doing a third-order system, this is where I need to take just a pause for the 1 or 2 people who might be doing third order. So if you look over here on a third-order system, the difference between this and that is that there's an extra bit over here with the speaker. So you can see it's very similar. It's an inductor with a capacitor, but then there's another inductor with the speaker. So everywhere you see the speaker, instead of just saying 4, in this case, I would write 4 plus 2 pi f times 0.11 times 10 to the negative third J. Because it's 4 ohms plus this is the inductor, and that's the inductor formula. So everywhere where I wanted to do this path, everywhere where the speaker would be, I also have to add in that inductor. So this place right here that says 1 over 4, this would be 1 over, big fraction, like 1 over, and then underneath that whole fraction would be 4 plus 2 pi, blah, 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 blah. If it was a capacitor, then it would be, it wouldn't be plus, it would be minus, because the capacitor formula is negative, so it would be 4 minus 1 over blah, 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 j. So you just need to know that if you're doing a third order, that's what you got to do. You just have to take your speaker, wherever you see your speaker number, and it gets added to whatever's in that line with it. Okay, if you haven't written these equations, you need to pause the video right now and get this done, because we're about to transition to Desmos. You finished? Because here we go. Okay, so now I'm over here at Desmos. What I'm going to do is open up the graphing software, and I'm just going to type in like exactly what I see here. So I'm going to write V out equals, and then I'm going to write absolute value, okay, fraction bar, and this is really key to do the fraction first, because this giant fraction, I want to tell it what's on top of that giant fraction, what's on the bottom of that giant fraction. I don't want to take the risk that I type things out of sequence. So I just type the fraction bar first, and then I'm just going to copy what's in there. Now, a reminder, we've done this before, we can't type the letter F in for frequency, we have to use the letter X for it to graph. And we can't type the letter J in, doesn't know what to do with J, I need to type the letter I for the imaginary number. So those two changes, but otherwise I'm just copying my equation here. So I got 1 over 8 plus 1 over 2 pi x times 1.5 times 10 to the negative third I instead of j, and then this whole thing is in parentheses to the negative 1 power, and then I can take this thing, copy it, and then go down here, and down here was negative 1 over 2 pi x times 5.6 times 10 to the negative 6, and then the I is on the side here, and then I'm going to go plus and paste that giant top thing in. Okay, and what does it say I just did? You need something on both sides of the minus symbol. Oh, did I not put a 1 in there? Okay, now I'm freaking out. Where did I do that? Where did I go wrong? I'll figure it out. Okay, I'm going to pause. Okay, so my whole problem was at the very end of the equation, somehow I'd gotten a minus in there. I don't know where it came from, but it was in there. Now, when you're done with this first equation, it might be like, hey, add a slider for I. Do not click that. We need to come over here to the wrench icon, and we need to do a couple of things now to format our graph. Number one is we need to click complex mode. That will allow us to graph things that are the absolute value of something with I in them. The next thing we need to do is click more options, and both need to be logarithmic. That's how we perceive sound. Now, the X values are going to go from 20 hertz to 20,000. That's human hearing. The Y values are going to go from 0.001 to 10. 10 times louder it would be pretty significantly louder, and none of our crossover systems are going to go that loud. And anything 0.001 is 1/1000th of a volume, and by that point, your perception of that frequency is basically like you can't hear it compared to the other ones. If it was the only thing there, you could hear it, but once you got all the other ones playing, you're not going to hear it. So this gives us a range of like what we would actually hear. Okay, and then when I do that, I've got it in logarithmic, I've got it in complex mode, boom, I can see this graph here, and it should look like this, where the high frequencies are here at 1, they're playing full volume over here at the high frequencies, and the low frequencies are basically gone because this is my tweeter. I don't want to play thumping bass through a tweeter. And so that's how the circuit should look. This is a second order system. If you had a third order system, it would be even a sharper, a steeper like cutoff. It would be flat, and then it would drop more quickly. Okay, and we're just going to keep going. I'm going to type in that low frequency one, which here's a pro tip. I'm going to copy in this one. Okay. I'm going to change this color here. Let's go blue for low frequency. Okay, and now all I need to change are some of these values. So here, if I look at it, is 1 over 4. And I'm going to take my head out of the way so you can see this. So the speaker was was 4 ohms instead, so I changed that to 1 over 4. And then this down here at the bottom is no longer an inductor, it's a capacitor, so it goes negative 1 over 2 pi x times, and then what's my capacitance, 55 times 10, shift to the negative 6, and then my I goes to the side this time. And then I'm going to take this guts of this, and I'm going to copy it down here. And you can see what's happening in real time as I update these graphs. Go like that, and make sure that guts is changed. And then down here, well, now this is an inductor, so it goes 2 pi f, or x, sorry, times, the inductance was 14 times 10, shift to the negative 3rd power, and boom. Once I'm done there, now I've got a low frequency roll off here. So it's flatter, it's at 1, down at these low frequencies, and then it begins to roll off there for like a subwoofer. And if I want to know that I've done it right, well, actually it depends on the type of crossover, I guess. But I should see my crossover frequencies were 180. So let's see here on 180, I get about 0.25, and my other one was 1,800. So let me go to 1,800. And that's about 0.5. Something's off. I feel like this should be higher, about 0.5. So maybe there's something up with my graph, or maybe when I did my calculations, I wrote the wrong thing down. I think they should match. So I'll check that. I'll see if there's any errors there. But for now, I'm not going to worry about it. Okay. Let's go back to the paper. Okay. The next thing you're going to do, and I'm not going to do this for the sake of brevity, is you're going to sketch that graph. So I'm just going to start it. So you would just go like this. And I would go 1, 2, 3, 4 up. And the third one is our 1, 10.1, 0.01, which means the bottom one is 0.001. And then this is at 20. And then I would mark where 100, 1,000. Oops, sorry, and then now 10,000. Where those should be, and then 20,000 is going to be pretty close here. 20K is where we end our graph. So we don't actually need it to go that far, just to 20K. Okay, and then I want you to sketch an accurate graph. Do the same thing over here as well. So you're just making a chart here of the y-axis from 0.001 up, up by multiples of 10 until you get to 10, and then here this starts at 20, and then mark 100, 1,000. 10,000 and 20,000 is the end point. We don't want any graph past 20,000 because you can't hear it. Okay. Now, at that point, if you've done this, that's a median level graph like work. There's some more analysis that we'll need to do, but the bulk of the work is done. We'll get to build it too. I'll show you how to build it and all that sort of stuff. But as far as like the really tough mathematics, the bulk of that work is done. And so if you've done a third order one, then you've got a more complex thing, and then you really are done. But if you're doing a three-way system, well, we've got the mid equation to do. And that one's a doozy. So first, let me show you why it's such a doozy. Okay, so here's the mid equation. Where's the speaker? Where is the sound coming out? And it's right here where it's labeled V out. So the speaker's connected to ground, which is nothing, 0, not moving. And then the V out is the thing that's moving, that's causing the speaker to move. So that's the spot. But here's the problem. it's inside of a voltage divider that's inside of another voltage divider. I'll show you. So if I look at this right here as Z1, as I have been doing, and then I look at this here, oh wow, that was really bad, Z2, that means right here is V out, not right there. So I could write that equation. But then if I just ignore that part of the circuit and I look at here, well, that's this, I mean, look, that's the same circuit as this. We know how to write that one. And so this is where it really comes into play, the full equation. So you see the full equation is Vn times, and we've been just saying Vn is 1. But not in this case. Here, our Vn into this little circuit is the V out of this whole circuit. So the V into this circuit is the V out of this big circuit where that's Z1 and Z2. And so really I just need to do the big circuit, that becomes my new V in for the next one, and then multiply it by that little circuit, which is just like doing this one again. And then there we go, that's our equation. Now, okay, that's a lot of stuff to write. Here we go. Okay. And you can see this, the equation's written out on the whiteboard as well, but I'm going to do it here for you. Okay, let's see if I got enough space to show you where my work is coming from. Okay, so again, and I'll write it over here. It goes V out equals V in times Z2 over Z1 plus Z2. And our first V in is 1. It's just 100%, that first V in. And so then I'm going to treat this to find this V out. I'm going to call this V out 1 and this V out 2, just to be consistent with what's on the whiteboard. Okay, so my V out 1 here is going to be 100% or 1 times, so I don't need that. And then I'll do this. And so Z2 is this giant network, which has this path and this path, which gets split into another parallel path. Okay, so I got parallel path. So how do I do that? I go 1 over the first path, which is an inductor, so 2 pi f times 7 times 10 to the negative third j. That's that path. Plus, well, my voice is really starting to go. 1 over this other path, which this other path starts with an inductor, 2 pi f times 0.6 times 10 to the negative third j. That's that inductor. And then in a row, so it's in series with this parallel path, which means I add it. So then I go plus, and now I realize, wow, this fraction is not large enough because the thing I'm adding is a parallel thing, and I'm going to need to use parentheses. So I got to go 1 over one of them. So I'm going to go 1 over the speaker, 1 over 4, plus 1 over that capacitor. So 1 over, and oh boy, the formula for a capacitor is a fraction, so I have a fraction down here, 1 over 2 pi f times the capacitance, which is 55, times 10 to the negative 6, there, j, make sure that fraction goes far enough. Oh, this fraction I underestimated, to the negative 1 power. Okay, and oh yeah, this was a parallel pathway, the Z2. So then I need a big parentheses here and a big parentheses here to the negative 1 power. And so this is why you can see why it's succeeding. So I did 1 over this pathway, and then 1 over, and all of this here, all the rest of this is this other pathway, which starts with the inductor, that's this, plus, and then this part is parallel. So it's 1 over 4, that one, plus 1 over this one, which is capacitor, so that mess. The good news is that you do not have to write this again. Like, we wrote it once, so we'll just reference it with the word top, okay? And then all over, so that was Z2. The bottom is Z1 plus Z2. Z1 is this part, which is a capacitor, so negative 1 over 2 pi f times 150 times 10 to the negative 6 j. That's Z1 there, Let me get to there. So there it is. And then plus that top piece all over again. So what I just wrote was V out 1. Okay? Okay. Now I need to find out V out 2. Well, V out 2 is actually simpler. V out 2, the input to V out 2 is V out 1. So instead of V in being 1 here, it's just V out 1. So V in is V out 1 times. So V out 2 is equal to V out 1 times, it's equal to this whole crazy thing, which I'm not going to write again, times, and now I'm just looking at this circuit. Just that circuit. I'm ignoring all the rest of it because I'm just looking at starting from here going this way. And that's identical to how we wrote this equation. So our Z2 are these two parts, our Z1 is that part. Okay, so to just recap there, I'm going to do fraction bar, parentheses, I'm looking here, this is my Z2, so 1 over 4 plus 1 over that capacitor. This is negative 1 over 2 pi f times 55 times 10 to the negative 6. J on the side of the fraction, and, okay, to the negative 1 power. Well, that was kind of sloppy, but it's much clearer on the whiteboard. And then our Z1 here is that inductor right there. So then I go 2 pi f times 0.6, I'm getting it from that inductor, times 10 to the negative third j, plus, and I'm just going to write top, meaning top of this fraction. Okay, oops, top of that fraction. And then this whole thing gets absolute value at the end. Okay, because that's what I want to graph. So when I type it in Desmos, I'm going to type this whole mess, and the top just means copy that and paste it again. And then at the end of this thing, I'm going to write times, because that's what it says to do. Take V out 1, this whole mess, times, and then I'm going to write this whole mess. And then around the entire thing, one absolute value at the very beginning, one absolute value at the very end. Not in between, beginning and end of that whole giant equation. And if you type it in correctly, you'll just get an equation that looks like this. Like a graph that's the middle. Okay? Doesn't have lows, doesn't have highs, it has the middles. So that's all where I want you to go today. If you need help, I'm hoping to be back on Wednesday. You can come in during the second half of mentor group or during lunch. And it's possible I'll have some time after school. I'd love to get at least a couple of these projects done so we can put them on the showcase and actually build the speaker. If you finish the graph and you're like, oh, it's all perfect and done, you can come in, have me check it out, show you how to build the speaker and like finish some things out so you can have it on display for a showcase. But anyway, that's the long of it. That is plenty to keep you busy for a day. All right, I'll see you, if not on Wednesday, on Thursday.